Hello, this is homework for part B for PDC, and what we're going to do today is explain the principle of bode frequency stability analysis from the practical viewpoint of a microphone and speaker feedback. Why is the amplitude ratio at 180-degree phase lag relevant? And we're going to algebraically show how substitution of S equals JW into the open loop transfer function yields amplitude ratio and phase lag in a bode frequency response analysis. And we're going to simulate the first order system to sine input and explain the early time behavior and compare the magnitude ratio with that obtained from a bode analysis, and derive analytical expressions for the amplitude ratio and phase lag of a first order system with proportional only control, and also that of a pure dead time system. So for the first one, I've already got our little diagram written or drawn. And so what we're going to label is our input and our output. And what we're going to be looking at is phase lag, which is represented by phi. So how this relates to amplitude ratio is if phi is less than 180 degrees, then our amplitude ratio will also be less than 1, and this is when it's very ideal and you won't see the feedback. However, if it's greater than 180 degrees, then your amplitude ratio is greater than 1, and that's when you will find feedback and it starts screeching and playing not the stuff that you want to play, and it's going to be very off. Now for the second part, what we're going to do is we're going to draw another diagram. So start with our Y set point, and then there's going to be like a little controller right here. This is going to go into our G sub C, which goes into our G sub P, and there's going to be an output, and then this connects to our G sub M, and then this will be connected to our controller, well, via signal. And basically what G is the product of our transfer functions. And so next we want to use this product of transfer function to find our transfer function to solve algebraically. So we're going to utilize basically transfer decomp to then get G times omega over S squared times omega squared, which equals A1 over S plus B1, I believe, and then we eventually get A2 over S plus B2, and eventually we will get CS plus D over S squared times omega squared. So what we're going to do now is basically try to convert this into a Laplace transform to make it easier to solve algebraically to find our value that we need. So also this is a plus S squared plus W, or omega squared. Thought it was multiplication, but it's actually addition. So what we're going to do now is we're just going to multiply this both sides by S squared plus omega squared, and that will basically cancel out these um, parts of it, and then we're going to be left with GW equals A1 times S squared plus W squared over S plus B1 plus A2 times S squared plus W squared over S plus B2, and then CS plus D. And because these components will be 0, we can basically just cross it out. And as stated in the problem statement, our S will be equal to JW. So we're going to make S equals JW, and also, J equals the square root of -1, or in this case, imaginary numbers. So what we're going to be left with is A times GW, which equals C times JW plus D. And so now what we're going to do is make this G equal KC K over tau S plus 1, which we're also going to go ahead and expand to tau JW plus 1. So if we plug that in, we get AW times KCK over tau JW plus 1, which equals CJW plus D, and we're actually going to multiply this by the complex conjugate minus 1. This is conjugate. There we go. So now what we're going to do is actually just get rid of our conjugate, and basically what we're going to do is multiply both the numerator and denominator with 1 minus tau JW. Also, I got it wrong again, so it's flipped. Instead of tau minus 1, it's the other way. So we end up getting AW times KCK times 1 minus tau JW, or omega, and get 1 plus tau squared omega squared over, or equals C j omega plus D. And then if we expand on, we get KCK over 1 plus tau squared omega squared plus negative J times, I believe, tau W times KCK over 1 plus tau squared omega squared, which equals C j omega plus D, and I'll have to double check if that is correct. And so now what we're going to do is this right here will be our real values, and this right here is imaginary. So we're going to label that as R equals KCK over 1 plus tau squared omega squared, and I, which equals the tau W KCK over 1 plus tau squared omega squared. And what we want to do is C will be equal to AI, and D will be AW times RR. So then essentially what we get is AI times RS over S squared plus omega squared, and AR times W over S squared plus W squared. And within our Laplace transforms, this section right here is our cosine, and this is our sine. So if we expand our equation, or I guess simplify it, what we'll get is AI times cosine of omega t plus AR times sine of omega t. Then we can just pull the AI out for simplification. Just rewrite this equation. There we go. So now what we're going to do is define h, which equals omega t, which is going to be here. And what we're going to get is a hat times sine of h plus phi. And a rule for like a sine times like a plus b, suppose, is that it becomes sine a times cosine b plus sine b of cosine a. So it's a bit of a interchangeable expansion. So a hat times sine of h cosine of phi plus a times, or a hat times sine of phi times cosine of h, where this is our real value, this is our imaginary, so r will equal a hat cosine of phi, and I equals a hat sine of phi. So we'll get r squared plus I squared, which equals a hat squared times negative cosine squared phi plus sine squared of phi, which then what we get is our a hat squared equals the square root of r squared plus I squared. And that basically concludes our algebraic derivation, or algebraic, I guess, simplification of our equation and what we wanted to find. Also, one more thing, if we take our I over r, it becomes a hat over sine phi over a hat cosine phi, which is just arctan. And this is just stating what phase lag is, essentially. So it is the arctangent of I over r, and that actually concludes the second part of B, or part B. So now we're going to move on to Colab, where I believe we're going to be simulating the response of a first order system to a sine input. Okay, so now for the coding section. Forgot to put my keyboard, but it's fine. I've got our library set up and our initial values for kc, k, tau, and omega. And so we're just going to do our G, and we're just going to define it, which we've already done previously, which is KCK over tau times S plus 1. And then we're going to define T and H, which will be what we use to graph. So this will be sim G lambda T and 2 times NP dot sine of omega times T, where N equals 1000 and dt equals 0.5, and then fig equals make underscore subplots, and this is relatively a shorter code today, where x equals t, y equals h, and our mode is lines, and that is it. So shift enter, this should work. There we go. So this is our sine graph and our oscillations. One thing to note is our first oscillation shoots up pretty high above 1, and then our oscillations later on reach a more of a steady state where they don't go past around negative 8 or 0.5, and it just kind of oscillates between that with, like, I guess, slight differentiation in values, nothing too crazy. Yep. And then we're gonna start the next graph. Now I want to look at is the Bode analysis. So fig magnitude angle, which equals Bode G, so relatively simple code. And basically what we get is we see the magnitude, and on our first graph we can see that it's a pretty steady decline, nothing too drastic. And then for our second graph we can see there's a dip, which kind of lines up with our magnitude for our top graph here, where we do see a rapid decline here, or I guess a change in our y-axis. So there we go, that's our Bode analysis. So now what we're going to do is derive the analytical expression for the amplitude ratio at phase lag of a first order system with a proportional only controller and with a pure dead time system. So we're going to go ahead and restate our transfer function, where we get kc times e to the negative s theta over I believe tau s plus 1. I could be wrong about the s. I'm going to get rid of that. I'm going to have to check that again, but we're going to go ahead and redefine our s equals jw, or j omega, and our j equals square root of negative 1. So our g equals kc times e to the theta times j omega over tau plus 1. Okay, so now what we're going to do, let's go ahead and define our e value, which we get cosine of omega theta minus I times sine of omega theta. Also, there was an s after tau, and I just I don't know why I thought there wasn't, but there is. And if we recall our a hat, oh, sorry, one more thing. We're going to define this as our real value and this right here as our imaginary, because we're going to recall that our a hat equals square root of I squared plus r squared. So this gets expanded to, once we substitute, cosine squared of omega theta minus, or sorry, plus sine squared of omega theta. Since this is also imaginary, we don't include the I. And then we also want to call our phase lag is equal to our arctan of I over R, which, since omega theta, we can just make it arctan of sine over cosine, which equals our omega theta. Okay, so one thing to add to the a hat, it equals 1. So there's that. And then if we recall, r equals r. We found these beforehand, so I just rewrote them just for ease of time. And then what we're gonna do is essentially just plug our r and I values both into our amplitude ratio and phase lag. So if we get a hat equals kck over 1 plus tau squared plus negative kck tau omega over 1 plus tau squared omega squared, and then this eventually just equals kck over 1 plus tau squared omega squared. And so this is our, I think it's called amplitude ratio. Yes, so this is our amplitude ratio, and then our phase lag, which is arctan of I over R. And if we can see right here, if we put I over R, we get this crossed out, and then kck and kck will be also crossed out. So then what we end up getting is arctan of tau omega. And then this right here is our phase lag. So we just successfully derived an analytical expression for the amplitude ratio and phase lag of a first order system with proportional only controller, also that of a pure dead time system. Actually, one more thing, sorry. I forgot to include this negative sign, so it's actually arctan of negative tau omega. So that finally concludes what we need to find.